Hi, everybody. I want to kind of summarize the week since I've been gone for a couple of days, and I've been posting things on Canvas. So this is not anything new for remote learners, but this is my strong suggestion for remote as well as everybody else on a daily basis, that you make sure you go into Canvas and look day to day at what's supposed to be happening. Yes, this is strongly encourage for those of you that are in class and things seem to be normal. You are missing out on a lot if you're not looking at the things that are posted on Canvas, like videos that supplement what we do in class, and solutions and things like that to work that is being done in class. So far this week on Wednesday, I posted an intro to Hooke's Law link. It was this page here, and basically this is exactly what it should have looked like as, kind of outcomes from your lab. You got a linear graph. We were instructed to look at the slope of our graph and what is the outcome of that slope, or what that slope tells us is how many newtons it takes to pull apart a spring or compress a spring if it's a squishy spring by a meter. So this one, the slope was 200 over, if you simplify it down, 20 over 0.1 is 200 newtons over 1 whole meter. So just simplifying it by putting it in your calculator is the best way to state a slope. Not 20 divided by 0.1 is the slope, but turn that into 20 divided by 0.1 in our calculator, you get 200 newtons for every 1 full meter. So that is a representation of how stiff or how difficult it is to stretch or squish a spring. And in the worksheets that followed the lab, I talked about that. And so you should have looked at those videos posted on Thursday and Wednesday and Thursday. And so today, I'll refer you also to the learning targets that were linked on Thursday, and the ones that I talked about that you should take notes on in your notebook. It says right here, learning targets 3 and 4 on the learning target sheet. So by looking at the videos, looking at the solutions that I've posted, I'm describing, just like I would in class, what the key ideas are, and you should be taking notes in your notebook. As if you were sitting in class instead of watching, some sort of video being presented on a computer. It's the same difference for us right now, unfortunately. But you should be recording that information in your notebooks. Don't try to live on the fly. Always trying to tackle a certain day's work off the top of your head. Have these notes written down for future reference. So today I'm going to jump to worksheet 3. And kind of quick run through the answers to this thing with some insight and detail into kind of the thought pattern for this stuff. So remember Hooke's law, F equals KX. I'm going to drop the triangle and the delta X thing because as long as you recognize that the X represents how far the spring is displaced, we don't have to put in the triangle and call it displacement in that formal way. Somebody kind of astutely pointed out that on some sites and in some pages, there's a negative sign in front of the KX. All that is referring to is the fact that the force that the spring exerts to try to pull itself back into its normal length, that force that spring exerts is in the opposite direction. The negative means the opposite direction of the displacement. I don't care about that. I'm not going to worry about the negative sign. I'm going to simply use F equals KX because all I care about with us right now is saying that the force magnitude, the amount in total, is simply calculated by the spring constant K times the X. So in running through these, if you want to make sure you don't make a mistake and put things in the wrong place, do what we always do. In this case, it says the spring constant is 2 newtons per meter. So K is 2 newtons per meter. That means it takes 2 newtons to stretch it by a full meter or change its length by 1 meter. In this case, if the X is going to be 5 centimeters, there's a reason why I always write this stuff down. If you see something like this, there's 100 centimeters in a meter, there's a reason for that. I don't just love stating facts like that. It's there because we have to convert this into meters. So because there's 100 centimeters, 1 meter has 100 centimeters in it. If we divide by 100, 5 centimeters becomes 0.05 meters. And I told you when you did the lab, and I mentioned it in the lab handout that was posted in the assignment for online people, we have to do distances for the spring stretch in meters because the K spring constant is in terms of meters. So we can't mix meters and centimeters in the same equation. So getting to the solution from this point is pretty easy. The force exerted on the spring, which is the same as what the spring exerts back, is going to simply be the multiplication of our K and our 5, or our X. So if K is 2 newtons of stretch or of force to stretch a spring by 1 meter, and our distance that we're stretching it is 0.05 meters, the meters cancel out because 1's in the denominator, 1 is not. Then the force from the spring is 0.1 newtons. Moving on to the next one. This time the spring constant is 0.5, 0.5 newtons to make that one stretch out by a meter. So the smaller spring constant means it's a flimsier, easy to stretch spring. In this case, it's going to stretch out by 0.5 meter. So there's no rhyme or reason why both of these digits are 0.5s. Don't think anything special about that. Probably not the greatest choice of numbers because it could make people think that there's some sort of connection, but there's not. So the force of the spring in this case is still just the simple K times X. And when you plug in the 0.5 times 0.5, the final answer is 0.25. And so if it's the force again, it's still a newton for a unit. And that's your answer, 1/4 of a newton. This one kind of throws a couple little curveballs at you. This time the spring is stretched 6 centimeters, and 6 centimeters converted to meters is 0.06 meters, like above. The mass of this thing is 200 grams. You notice the inflection in my voice there. 200 grams is not the force. Remember, it's a mass. And if we're going to hang this mass, say this is the ceiling and there's a spring hanging from the ceiling, and we hang this thing, maybe it's a fish or something like that. The force that it exerts on the spring is the force of gravity. So we have to change this mass to the force gravity will pull on it because that's what's pulling our spring here. And so remember, M times G will lead us to 0.2 kilograms because that has to be in kilograms. So 1 kilogram, 1,000 grams means move your decimal 1, 2, 3 places to the left. When we divide by 1,000, we pull the decimal 3 places to the left. So 0.2 kilograms. That's where this comes from. And G is 10, if you recall all the times you had to do that. So in this case, the force of gravity is what's pulling the spring, and that's going to be 2 newtons. So what do we want to find here? We want to find the spring constant this time. Calculate the spring constant. So K is what we're looking for. So going with F equals Kx. Okay, recognize that this is the force that we're putting into the Hooke's law equation, the force of gravity, because that's what's pulling on the spring. It's that weight of that thing. So 2 newtons K is what we're trying to solve for, and our X is 0.06 meters. And basically, once we divide both sides by 0.06 to solve for K, then K becomes 33.3 repeating. And if newtons were the numerator force and meters are the denominator force, this is newtons per meter, like we saw in the given ones before. And like the website that summarized what you should have seen in Hooke's law described as the slope, and the slope was newtons on the y-axis divided by meters of stretch on the, newtons on the y-axis, meters of stretch on the x-axis. So rise over run units, K has newtons over meters. That's where those come from. So continuing on from question 3, this time our new mass is 500 grams. Convert that to kilograms, and that is 0.5 kilograms. We have to use that because our new force of gravity is based on that. So that'd be 0.5 kilograms times 10 for gravity. Gives us a force on this hanging spring of 5 newtons now. And it's the same spring. Putting a different weight on it doesn't change K. So here's our force that's on the spring. Our K that you just calculated should have been 33.3 newtons per meter. So if we want to find our X, go to Hooke's law, F equals Kx. Plug in our numbers. 5 newtons. K is 33.3 newtons per meter. And solve for X. So if we divide both sides by 33.3 newtons per meter, everything cancels over here, obviously. Divide by 33.3 newtons per meter. And it's a little trickier to understand how the units cancel, but these newtons would cancel the numerator in the bottom, leaving 1 over m in the denominator, and invert and multiply, and meters come flying out of the bottom and become just meters on our answer. And our answer is 0.15 meter equals X, or the stretch amount. That's the same thing as saying 15 centimeters. You don't have to convert back to centimeters. I'll take 0.15 meters all day long. But that's how you work with Hooke's law. Hope this was helpful.